I don't have control over that.
I'm basically taking 3 4 credit hour classes. This is almost, I've literally, the workload is a 4 credit hour class, the workload right now.
You said what?
This class is
I don't know that that's true for everyone.
Yeah, for Whitney.
It's not, right? Well, you've only had 2.
I had the best 2 math professors at this school.
Who are they?
You
I
know
don't know,
nothing
I
else.
like Mr. Thomas.
I don't know. My husband is fine. Yeah, that's fine. That's fine. He's pretty good.
Yeah, I like y'all both equally.
If you like him better than me, that's fine.
No, I don't pick favorite math professors.
I felt that.
I had a favorite math professor. I had 2 actually.
I've only had the Thomases and Reeves.
Never mind.
I had a bunch.
People are scared of Martinez. A
People,
lot of people are scared of Martinez.
yeah, that's fair.
I've had almost every single professor.
Well, right.
Oh, they'll have them for promise hats.
I'll have her husband for history. What's that?
I remember.
He loves that class.
Yes, he was getting
He
so hyped.
loves that class.
Yeah, he was like, y'all should come on, like they're doing a presentation today on the
Their
history of-"
presentations, when next time that happens, y'all should go. Their presentations the last time it happened, which would have been when he was with y'all. They were fantastic. Every single one of them was hysterical. And you think like, there's no way. But like actually they were, and all of them, it's like they had some agreement, like we're gonna be funny when we do these talks. And they did so well. They were hilarious.
He never made it sound too intriguing.
No.
Do y'all want to come watch the presentation?
No, we don't, thanks. No, I get that totally. But I, went to support him and the students, and I'm so glad I did. I actually learned stuff and got to laugh. It's a win-win, All right, so today we're gonna continue doing induction, and then hopefully we're gonna do strong induction. Now, I told you guys to try your homework before today, so that your homework was what it was intended to do, which is see if you know what you're doing. And did you do your homework? Did you try to do any of your homework?
I
Oh,
cried. I cried.
That is not what I was talking about.
I cried.
The paper homework, written homework, number 9. You didn't try it. You did try it.
8.
Good, I have that. How'd it go, Sky?
I noticed I had trouble with the step, like in the groups, like in that part, like
I didn't.
Okay. Okay, well, we'll do a couple more today, and then we'll do some strong induction and see where we are. Okay. I think I fixed all the dates, except for you asked for an extension and I ignored that. Sorry.
Okay.
It fell down.
At midnight tonight, so.
That's when you asked for it?
Yeah.
Okay, I'll go do it when I leave here. Okay. I think I fixed the dates for everybody else in WebAssign. Are your WebAssign grades going into Blackboard? Well,
Let's keep it that way.
okay, so they did at some point and stopped? Oh, why?
Yeah, after like 4, I think it's 4.3 was the last one. We're on like 7 something now.
Y'all know that I'm doing Blackboard Ultra with 3 different online platforms this 4 different online platforms this semester. 3 with my math lab, Pearson, Cengage, WebAssign, and with Hawks. And they're all different in how they interact with Blackboard, and I'm totally confused. So I would love for us to just use one software all the way up, but that's not my choice. Above my pay grade, like my colleague just told me, everything is here.
Oh, wow. Ooh, that's nice.
And not wrong. So that's fine. So we have this one, number 5 here, n is greater than or equal, if n is greater than or equal to 1, then 2 divides n squared plus n. There is one in particular, Ruth worked on it for a while in the office this morning. There is a problem on the homework in particular that is kind of tricky, and you have to really like get creative with it. So, but it's a divides one, so we'll go through that now, and see where we are. So induction, remember, we are trying to get on the ladder, so we're trying to get on that first ladder rung. And then after that, we want to suppose that we're on any ladder rung and get to the next one, show that we can get to the next one. So for the base case, what should we look at here?
Well, if n is greater than or equal to 1, let's just start with n equal 1.
Good, so we're gonna let n equal 1, and we're gonna look at n squared plus n, that's 1 squared plus 1, which is 2. I think that's the fine place for a clearly, don't you? 2 divides 2, so base case holds. Wait, that handwriting is really bad. If Logan's watching in Zoom, he's gonna be very judgmental.
Okay, all right.
Um, Okay, so for the inductive step, we're gonna assume it works when n equals k. So you're gonna say for some k greater than or equal to 1, that 2 divides k squared plus k. What does that actually mean? It's even, yeah. That k squared plus k is equal to 2 times an integer. Right? I don't know what that integer is yet. My husband said I make my k's weird too. I asked him last night. He said they're weird. My husband, he does his k's without picking up his pencil.
That's weird. Well, that's weird.
I mean, his looked better than mine do. He said, there we go. He says that I often like don't write the tall part, or it's like not there, so it's not clear what's going on. I don't know. But he said he sat in on this class twice.
I have thought it was an and something. before.
Yeah.
I have-
Yeah. I mean, I'm with you. That doesn't look anything like a K. But it is one. Okay. So it looks like a tiny little R, doesn't it? Whatever.
No.
Okay, so for some k greater than or equal to 1, 2 divides k squared plus k. So that means that k squared plus k is 2 times some integer. I don't know what that integer is yet. It doesn't matter yet. What I want to show is that this works when n is k plus 1. So what that means is that 2 divides k plus 1 squared plus k plus 1. Why that 2 is so little. And what does that mean if 2 divides k plus 1 squared plus k plus 1? Is even, yeah. So k plus 1 squared plus k plus 1 is equal to 2 times an integer. This is the thing that we're going to try to show. This between these two things is where our proof is. Okay. So I'm not gonna do anything else over here right now. I'll do it in the proof in a minute. Anybody want to start narrating here?
You got
I
it.
want to do it.
Take it, Ruth.
We will prove by induction that n is greater than 1 and 2 divided into.
Okay. Close enough to what I would say. Good.
For the base case, let n equal 1. Notice n squared plus n equals 1 squared plus 1.
I'm not gonna do all of that, but that's mostly because I don't want to do a whole bunch of lines.
Clearly
Clearly what?
2 equals 2. Oh, 2 divides.
That's what we're trying to show, right? Oh, I took some sinus medicine. Like, room is spinning a little bit.
Uh-oh.
Okay, I did that like looking up and down really quickly, and it was like, whoa, no. Don't do that again. Okay, so clearly 2 divides 2 is the base case holds. I'm good. I'm with you, Ruth. Keep going.
For the inductive hypothesis, assume that n equals k for some integer.
No, we're just gonna assume that 2 divides k squared plus k for some k greater than or equal to 1. The in stuff, like I'm doing this over here to help you figure out what we're doing and why we're doing it. Yeah, but I'm not gonna write that in the proof.
Okay,
I'm just gonna assume it works for the kth step.
okay.
Okay. So again, this is where we're gonna start. And then we're gonna do a whole bunch of crap in here to hopefully get to this point. Okay, so we're gonna do consider k plus 1 squared plus k plus 1. We're gonna work with this to make it be divisible by 2. Sound good? Okay,
We have k plus. Take a k out of the first one.
I can't take a k out of anything, Ruth.
Does not work with the k squared plus k.
Yeah, but I gotta FOIL first to do that, right?
Okay.
I'm gonna FOIL this k squared plus 2k plus 1 plus k plus 1.
Okay. let's see what it is.
And then if I group that, like you're saying, I get the k squared plus k there, then I have a 2k and a 2 left behind. Y'all tracking all of that? Rearranging things where I'm looking at the, okay, the k still looks strange.
We understand what it is.
That is real unfortunate. Look at this one. What's even happening there?
I think we understand what we're looking at now.
It just looks like I'm writing a C with a line.
Yeah.
Right? Like that's what this is, and that's what this is. Although I would never tell someone that a sent to Sembo. That's what I'm actually doing. I know. But like some of them are very pointy, like that one. That's definitely not a C.
That's an angle. That's
Mhm.
some kind of angle.
It's not an angle. Okay, all right, so here I just like group stuff, so that like Ruth was saying, this is the thing that I'm trying to use somewhere. I haven't yet. Hi, Charlotte. I probably should have put another line in here. Like right here and say, then, or we know, or something. By definition. K squared plus K is equal to 2 times A. A and Z. We good? Sorry, I'm gonna use it now, so I wanted to go ahead and say it.
Oh, okay, I see where you're going.
Right, if that thing K squared plus K is even, then that means it's 2 times an integer. I'm gonna go ahead and do that so that I can make the substitution right now. So this is equal to 2a plus 2k plus 2. That is 2 times a plus k plus 1. Yeah? No, yes?
I don't see. Oh, it's not.
The inductive hypothesis says that this equals 2a.
Okay.
The inductive hypothesis, you assume it works for the kth step. So assume it works for the ladder rung you're on and show it works for the next ladder rung. But that's always going to use the ladder rung you're on. Yeah. So we have this thing, we're looking at the next ladder rung, but we're trying to break it up into pieces where we can look at the ladder rung we're on plus the next one, right? So once we get this where we have something that looks like the ladder rung we're on, we can actually use our inductive hypothesis, the thing we assumed was true, to sort of get rid of to use the fact that we were on the ladder rung. And then do the next step. Yeah? Yes? Okay, and then you would say something like, since a plus k plus 1 is an integer, 2 divides k plus 1 squared plus k plus 1. So we have shown 2 divides n squared plus n for all n greater than or equal to 1. Well, why are you making that face? What's happening?
No, you didn't, so the last part was a different conclusion from what we did.
How is it different? What yeah, we did it. It's not different.
Okay. So would you be able to still say like the inductive hypothesis?
Oh, that's the inductive step holds, yeah. Yeah. I mean, I said that here, I just didn't say it in as many words, right?
Right.
Yeah. So 2 divides this thing, that's what we needed. And so, yeah, I did not say the inductive step holds, but it does. Yeah. Mhm. Yep. Apparently, they make bowls, a set of bowls that are the proof is in the pudding bowls. And they have like the proof that there are infinitely many primes is in one of the bowls. And I know it was pretty cool, right? Apparently they're on Amazon. I'm gonna look them up. But this is what I was saying yesterday, like you can't write these two things next to each other until you actually do the proof. And we're gonna call this little in-between part, like this is the pudding, yeah? This part right here is the pudding. That's where you have the opportunity to be creative sometimes, and that's kind of fun. Okay, are we good on number 5? It's very what? Yeah, it can be crippling, but again, if we're not uncomfortable, we're not learning, right? The stretching of our minds or our bodies or whatever, that's uncomfortable. But once you have stretched, it becomes more comfortable, right? $30 for 4 bowls?
I want to, where did you
Oh,
find that?
good. The proof is in the pudding bowls.
And they're very small bowls.
Yeah. Yeah, the person who was talking to me about it said it was like a dip bowl.
Yeah.
Like a personal dip bowl. Like, here's my peanut butter and my celery dip bowl. For $30. Okay, well, I will not be buying those for myself. Maybe I'll ask for them for Christmas. Okay, there we have that proof. Are y'all good? Ooh, I don't think I want to do this one. You do like factoring. You said that. We got to factor to get this to be, look, if we have to do this, we have to factor to get this to be k plus 1, k plus 2, and 2k plus 3. Oh, I'm not doing that.
That's amazing.
Can we do a proof that does have the signal notation?
We've done like 4. Haven't we? Yes, I did. Yes, yeah, 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 yeah.
One thing that confused me on the homework was when like the I was a 2I.
That's all it is.
Yeah. That's the, I will talk to you about that on this one, or I can.
That's all it is. It makes me so mad.
It's sort of like, it's this idea. The thing that maybe was giving you trouble was this step. And where the Cengage was asking you to like split up the first, the split up your like big thing into 2 smaller things. But the second piece is is not really a sum, because it's from it's from the K plus first step to the K plus first step. So that one's just 2 times K plus 1 minus 1.
I guess I'm used to doing it the other way. So
The-
I guess that.
Well, I mean, so looking at I tried to like show you guys this too when we were doing it. Looking at any sum from like I equals 1 to K plus 1 of something, right? You can split that into I equals 1 to K of that thing plus that thing with the K plus 1 plugged in, whatever that is.
Oh, like you plug it into the equation.
Yeah, right.
Okay.
Because you're doing the summation, but it's not really a summation because it's just that steps. You're not adding it to anything. You're just doing that one thing. Does that make sense?
Okay.
Like if this was n squared or something, right? Or I squared. Right, then this would be an I squared, and then this is just K plus 1 squared. Like all you do there is just plug it in, because it's not really a summation, because it's just that one last term. So this is like all of them up to all K of them, and then plus the K plus first.
Okay, because I was writing out the scratch part of it, and I'm like, wait, how many times that suits part? Like, I don't know,
Yeah.
for some reason, since it was like a 2, it was like
Yeah.
breaking my second.
Yeah.
I got to a point where I was like, oh yeah, I think I know what I'm doing, and then I got to a point where like my brain just crashed. It's like, ooh, I'm on the motorcycle, and then it's just like, crashed.
What a brutal and awful way to describe that.
Sorry.
Uh,
No, that's how it felt.
All right.
I enjoy violence, therefore I enjoy math.
This will probably, looking at this though, will help you, because like, I mean, I did that replacement in both places, but I think the thing in Cengage like did this with plus this thing. Like it was the K thing still in the summation, and then the K plus first thing, like not.
Maybe part of it was I didn't write down that part, I did the
Oh,
other part, so
yeah.
I was like, oh, I won't.
Yeah,
only
yeah,
need
yeah.
One of these, and I'm like, wait, we're gonna need more.
Well, did you did that? Yeah. Mhm.
Maybe that was part of it, so.
Okay. I'm not doing that one though. So for this one, we're gonna prove that, I think, here's the thing about these ones that are the divides or the less than ones. This is where I think we need practice and you need practice where, because it's not just chasing, you don't have everything that you need. These you have to put something in yourself. Yeah, like at the end of class yesterday, Tuesday, this is an example of that. Like when you're doing the summation ones, you're literally, it's plugging and chugging. It's replace this, find and replace this with this, and then make it look like the other thing. But you don't have to come up with anything. It's all there. You just have to rearrange it the way that you need it, right? With these, you have to come up with stuff to make it look like what you want. You have to come up with stuff that doesn't break math and make it look like what you want. Yeah. Like this, from here to here, this was pulled out of, my noggin to make it look like the thing I was trying to make it look like. Like this wasn't a thing that was there already. You get what I'm saying? So that's why we're gonna practice number 7 instead of doing number 6 again, because that's just like literally just changing algebra around, and I don't care for that right now. So we're gonna do number 7. So we are gonna look at if Oh, also, Ruth asked a question the other day about exponential growth being the fastest growing thing, or factorial growth being the fastest growing thing, or whatever. And that's true. She was not wrong, and I was not wrong. That's true if the base of your exponential is fixed. So in factorial over time is going to, like, eventually will grow faster than like 2 to the n or something when that base is fixed. But what we proved was it is always less than n to the n. So if the base is moving also, you can't say that thing. Yeah, okay. So 7, we have n squared is less than 2 to the n if n is bigger than 4. So what are we gonna do? I'll tell you, we're gonna do the base case. What's our first starting value?
1. No,
Wrong.
so 5.
Yeah, it's 5. N equals 5 is bigger than 4, so n equals 5. And you're gonna say something like, notice, now, what am I not gonna do? I'm not gonna plug 5 into both of these right there with that inequality. Right? I'm not gonna say 5 squared is less than 2 to the 5th is true. I'm not gonna do that, because that's ugly and I don't like it, right? So we're gonna say, notice 5 squared is 25. And 2 to the 5th is 32, clearly. 25 is less than 32, so the base case holds. Stating an inequality to be true when it's the thing you're trying to show is true is not a good form, yeah? Okay. What now?
Inductive.
Mm-hmm.
Or we let k n equal k.
Mm-hmm.
Which means it would be k squared is greater than 2 to the k.
That's less than 2 to the k for, yeah, some k greater than or equal to 5. Okay, and what are we trying to show?
But
That's the thing we're trying to show, that k plus 1 squared is less than 2 to the k plus 1. Yeah. And the proof is in here, right? That's the thing we got to fill in. We're not going to write those two things next to each other until we've actually done it. Okay. I'm ready to write a proof. Who, other than Ruth, would like to help me? Okay, Dan, go ahead.
To approve my induction. That n squared is less than 2n for some in
For all, we're doing it for all. Mhm.
n squared
For all n greater than 4, good, uh-huh.
for the base case. In 5. Notice 5 squared is 25. 2 to the 5th is 32. 25 is less than 32. Clearly 25
Some
is
word,
less
yeah. Now clearly observe or notice or huzzah. Clearly 25 is less than 32. So
the base case holds
good.
for the inductive assume K squared is less than 2K. Or some K greater than or equal to 5. Consider K squared is less than 2K.
So don't write that yet. When we do the consider step, we're gonna write this down. The want to show, the left side of the want to show. Mhm.
K plus 1 squared is less than 2K plus
And we're not gonna write that yet,
1.
because that's gonna be down here somewhere, yeah? So the proof part, we're gonna do, we're not gonna write those next to each other right now, because we don't know that, that's the thing we're trying to show, okay? But what do I know?
That K is less than 2K.
That this is K squared plus 2K plus 1, right? Yeah,
Oh, cause you foiled
I
it.
foiled, uh-huh. What do we know? I'm starting to think that medicine wasn't daytime medicine.
Uh-oh. Uh-oh.
It's all right.
The room spinning it.
Be a little. It's okay. I might need to sit down in a minute. We'll drink a little more coffee while y'all think about this. What do we know? We do. How do we know that, Whitney? We sure did. Our index hypothesis was that K squared is less than 2 to the K, so let's use it.
Oh, okay. So every time when we're doing this, your assumption and the inductive step is gonna be used somewhere in your math.
Yeah, that's the whole point. That part's the P implies Q. You need to use P to show Q. If you're on this ladder rung, you can get to the next one. You got to use the ladder rung you're on to get to the next one. Yeah. All right. Now, I'm trying to get this to be 2 to the K plus 1.
When you take it to, no, you can't. I'm not-
Foil out some of it too, sort of. It's on.
Okay,
Two.
so let's maybe like work a little bit backwards. We are looking to get like 2 to the K times 2, because that would be 2 to the K plus 1. Maybe. Is there a way that we can do that? No. What if I make this 2 to the K plus 2K plus K?
And why would,
I don't know.
what is the, why did you replace the one?
I'm just doing stuff. Why did I replace what? The one with a K? I don't know, why not? It's true. K is bigger than 5, so it's certainly bigger than 1. Right?
Oh, okay.
Oh, okay, so as long as it fits then.
As long as it fits, you can do it. I'm really trying to get another K squared there so I can write it. Maybe write it 2 to the K.
Well, we have a 2 to the K.
I have one of them. I need 2 of them. I need 2 times 2 to the K to get 2 to the K plus 1, because that's what I'm trying to get, right?
Mhm.
Okay. Would you agree with me that it's not an equal sign anymore? That this thing is less than 2 to the K plus K squared? Why?
K is greater than 4.
Mhm.
And so 3 times something would be less than 4.
The smallest that K can be is actually 5. So 3 times 5 is always smaller than 5 times 5, right? So 3K is absolutely smaller than K squared.
Okay,
And then I can use my inductive hypothesis again. The inductive hypothesis again is that K squared is less than 2 to the K, right? So I can just replace that one part with less than 2 to the K. Y'all, that's 2 copies of 2 to the K. That is 2 to the K plus 1. We did it. Well, we didn't write the end of this proof yet, but we're close-ish. I'm gonna drag this up into that other problem that it did not work.
It'd be really nice if, you know, on pen and paper, if you had anything.
Yeah, sorry about
Or
that.
you just run out of
Sorry
room.
about your life, Charlotte. I'm just kidding.
Oh.
I was doing vector addition and subtraction today in pre-cal. Then I was doing like to do vector subtraction. I like drew the vector and then made notability, like draw it backwards, you know, like I just drug it down. And they, you know, they can't do that. But I didn't tell them to draw it. I said, y'all just watch, this is cool. I don't think they did, but whatever. I don't think they thought it was cool. Okay, so once we do this, I know this is kind of all over the place and doesn't fit here, but whatever. So we're proving by induction that n squared is less than 2 to the n for all n greater than 4. For the base case, let n equal 5. Notice 5 squared is 25 and 2 to the 5th is 32. Clearly 25 is less than 32, so the base case holds. For the inductive hypothesis, assume that k squared is less than 2 to the k for some k greater than or equal to 5. We're on some ladder rung. Okay, we're gonna look at the k plus first ladder rung. So consider k plus 1 squared. We want to know, is that in fact less than 2 to the k plus 1? So we know it's equal to this stuff. And again, we're not breaking math. We're kind of trying to get creative with things. But we get to a point where we're looking at that k plus 1 squared is less than 2 to the k plus 1. We have k plus 1 squared is less than 2 to the k plus 1. So the inductive step holds. This is what you were talking about earlier, right, Ruth? And therefore, oh my goodness. N squared is less than 2 to the n for all n greater than 4.
I take a picture. I'm slow, right?
It's cool. I'm like halfway asleep, so it's all good. That proof?
Yeah.
Wasn't it kind of fun?
I don't really know what all is happening, but sure, it was fun.
With what part? I mean, the middle part,
The
yeah,
fact
yeah.
that you can just like, you know what? We're gonna just change everything now. You know what? One, forget about the one. It's now okay. And you know what? Now it's gonna be a 3. Oh, and guess what?
Ooh, ooh,
K squared.
that's right. It's kind of fun. This is not like a thing that you're just gonna come up with first time try, probably. You're gonna sit there and you're gonna think about it, like, what could I do with this?
I hate
Some-
creativity.
I
You
hate
hate
creativity too.
creativity.
I mean, it makes sense. Like, okay, yeah, okay, then the smallest thing to be is 5. Okay.
Yeah.
Greater than 1. Like, it
Yeah.
makes sense, but it's like,
How would I have thought
And
that?
it feels wrong. It's
It
like
does
when you
feel
said you
wrong.
can Put the E stuff in there. I'm like, what?
Yeah,
We can use symbols now.
why not? Yeah. Oh, sorry, yeah, when I do the element thing in the middle of a proof, when I told you not to do that.
I'm like, I feel like I'm going against everything I've ever learned.
I don't know what I know anymore.
This feels wrong to like change these things.
Oh,
It's
can we
like
go
I'm
to,
disrespecting the equation.
Let's keep practicing though. Cause don't you want more practice?
We do
So
want
I'm,
more practice.
I am not going to write a full proof because I don't want to. We're just gonna do scratch work. Cool?
scratch word, yes.
Fine. All of the fluffy words are the same for all of them. Yeah. So I'm not going to do them on this one. We're just gonna do some scratch work. What's the base case for this one?
Rose says you said not to write any proofs.
What? Oh, yeah. Please write proofs on your test.
Can we do like a general outline of a proof or more like absolutely,
Like, in what way?
like the words that we're supposed to use?
No, but you can write definitions. So like for 1-to-1, for all A, B, and X, if f of A plus f of B, then A equals B.
So we can't do like a proof outline.
No,
But like for.
this is your fault, by the way.
How is it my fault?
Yeah, yeah, because that's also the like definition, right? Like, I don't want you,
Yeah, like we
Yeah.
can write like, do the base case first and then do the inductive step for the inductive.
because you sat in my office with a proof that was correct. And you said, I don't understand this proof. And I said, you did that proof. How did you do it without understanding it? And you said, I just copied the other ones. And I said, oh, heck, that's a problem. We're not doing that anymore. The note cards the note cards are a relic of COVID, when there were people who were taking it virtually and people who were in the classroom and trying to like level the playing field, knowing that people at home probably were not just
Not being honest.
correct. And so it was like, if I just tell everybody they can do this, then maybe people won't be cheating and things, right? And it's just never gone away. But I don't want you guys, the structure of this stuff is kind of the whole point, right? So I need you to be able to do it. And I don't mind you having a note card that has definitions on it so that you can look at them, but I want you to be able to write the proofs for that stuff. But like that would help with the non-proof questions, right? Too. It helps with proof questions too, because you prove the definition works. But yeah, I don't want like a proof, like a detailed proof outline, like an induction proof. You do a base case and then you assume it works for k+1, show it works, or assume it works for k, show it works for k+1. That's fine. But like not a ton of detail.
That I did for one of note cards was instead like for the proofs and everything, I would do like the first word, like I'd do a let and then a therefore, like that kind of thing. Is that going on there?
I think that's probably toeing the line.
Okay. I just wrote the little beginning words. And I'm like, okay. Thanks for having.
Yeah,
me.
yeah. I think definitions are probably good because those words are built into the definition, right? If this is happening, then this thing is happening, right? So, but really, I just, the structure itself is a thing I need y'all to be able to do, and that's what I'm testing you on. So copying it from something else is not all that helpful. Yeah,
Felt like there was one proofs we did. where we had to
why are
do,
you
like,
sorry?
I was able to, that's just how it, I was able to use. do
I
another
know,
proof
I know,
based
and
on-
I know that that's happening, but the fact that it's like a thing that you also know is happening is bad. We gotta change it. It's not, I mean, it's not your, like, I don't mean that in a negative way, right? But we all need to make sure, all of you who are gonna have to take the computer science exit exam thing, like, this stuff you have to know. The people who don't do well the first time, often it is the math part. So I am trying to help with that, yeah? Yeah, because you're not gonna have no card then.
That's what all the computer architecture. See it, discrete.
Uh-huh. Uh-huh. Well, did they pass that exam? Don't know yet, okay. But yeah, I'm just saying, like, and it's gonna do you better in the long run too, when you're studying for your final and stuff, that you didn't have that like sort of crutch this time, because y'all don't need it. The proof that a function is 1-to-1, it's not a thing you need to write on your note card. You know how to do it. You don't need that crutch. You need to believe in yourselves. Yeah, that's what you need, is confidence. Yeah,
Yeah,
right, Logan?
Time.
take the chest.
Time.
Confidence that you know what you're doing, and it'll also save you on the time, because you're gonna be trying to figure out where you put this thing on your note card. You're just gonna do the thing. And you're not gonna second guess yourself because you're trying to find it on your note card. You're just gonna do it. It's gonna save you time. It's gonna save you, I don't know, stress and anxiety to making your note card. And yeah, it's gonna be more stressful maybe in the moment. But you'll have definitions and things on your note card, right? You're not gonna think, oh, why didn't I put this proof on there? Because you wouldn't put any proofs. Yeah. Yeah, I'm really putting this spin on it. Should I be a salesman? No. No, I should not. It did help me wake up just a little bit. But yeah, so, and it's, like I said, Ruth, it's not a bad thing. I probably shouldn't have said that it was your fault. I don't mean it that way. I just mean like, I probably shouldn't be doing it anymore anyway, but I don't want to pull out the rug from you totally, because you guys have had note cards in all of your tests, but next semester they won't, have them at all. But like, you know, we'll just move forward with, you can have a note card, but no proofs on it. Yeah, which is fine, because after we get through this, I don't think there are any proofs in the next set of notes. It is just for computer science people.
It's kind of easy.
Is what?
It's like the Morgan's law. of computer
Oh,
architecture.
Yeah, those things up there.
And the knots, yeah, that's what Jackson came in here, he's explaining it today.
Yeah, it's a finite
Course,
state
Jackson.
automata.
Yeah.
So Jackson, a finite state automata up there. He keeps emailing me to tell me when he uses discrete in his computer science stuff, and I'm like, thank you. Like, I need to know this so that I can tell people that it's not worthless. Okay, so we're gonna do scratch work here. Base case is when n equals what? I'm gonna look at this later and be like, what was happening? Also, somebody's gonna watch it online, like my friend who watches my videos for fun, while he's working for some reason. I guess to drown out other noise, I don't know. Okay. But he would try to listen to that, and I don't think he's trying to listen to me. Okay, so base case n equals 2, we're gonna say, oh, okay, well, 3 times 2 plus 1 is 7, and clearly 7 is less than 9, so it works. Yeah, I'm not writing this formally, right? I wrote that check mark. So the inductive hypothesis here is that for some k greater than or equal to 2, that 3 times k plus 1 is less than 3 to the k. For the inductive step, we want to show that 3k plus 1 is less than 3 to the k plus 1.
3K plus 1 is less than 3K.
How is that even possible?
That k is a small k.
It's an exponent.
This k is littler. It's not.
Why do you find a new variable that isn't K? I feel like this is just going.
Look how tiny it is now. I have to do what? Find a new variable to use.
Oh, I did, okay, I was like, wait a second. That doesn't, that makes it a little bit better.
Okay,
So what is it that we're wanting to show? Sorry.
I literally just wrote it down. It says inductive step, show this. That's what we're trying to show.
Then we do crazy math and then we just, it appears out of nowhere.
We do it like
I'm gonna choose to ignore you for a moment. Oh my gosh. What are those things? Okay, plus 1 plus 1. So I'm starting on the left. And I'm gonna move in ways that make me get to the right hand side. Yeah.
Okay,
Alrighty.
can you add? Oh, well, we can't. Can you distribute the 3?
Mhm.
Not 1. 3K plus 4, and 3K plus 4.
We're trying to do the K plus one. And,
K
Plus one is less than 3 to the K.
Um,
If we factor out the 3, then we can change it to 10, right? We're not through with it. So. So 3 times, wait, oh, wait. The little K thing must be.
It's little, it's little.
So can we do the inductive hypothesis, use the inductive stuff again and say that, well, 3 to the K is less than 3 to the K plus, or we just did that?
We did.
Wait, are we done? Because it's a third of the 1?
No, because this is adding, we need to multiply to do that.
Oh, okay.
Like doing stuff to the 3.
Okay, what do you want to do to that 3?
Break it up. Can we break it up and say plus 2 plus 1?
Why would we do that? Okay.
Dude, I'm lost.
That's not helpful, right? Like, I don't know what that would do for us.
That's not gonna help us? Then you had 3, but you're just, okay. But you're getting rid of that 3, aren't you?
Right, this thing, if written differently, is 3 times 3 to the K. That's where we'd like to be. That's 3 to the first times 3 to the K.
Oh. Ooh. Oh, so we want the 3 there.
I got 2 routes I could go with this. I just need to get bigger, right? As long as I'm getting bigger, it doesn't matter what I'm doing. Well, if I make that 3 a 3 to the K, it's gonna get bigger. Right?
Can we just-
Can we just do that? Is it gonna get bigger if we do that? So is it okay?
Let's add another 3 to the K.
To get to this, because we need 3 to the K plus 1.
So I still don't understand.
like taking out the 30.
I don't understand that.
I don't understand.
And the last one was 2 to the K, and we needed 2 of those. Like, on the last group, we had 2 to the K, and we needed 2 of those.
Because we needed 2 to the K plus 1. 2 to the first times 2 to the K is 2 to the K plus 1. So it would also work, Whitney, if you here, you wrote this as 2 times 3 to the K. Well, that's smaller than 3 times 3 to the K, so you could do it that way also. I mean, you're still, adding another one in there, but as long as you're getting bigger, it doesn't matter. You're not breaking the integrity of that inequality, so it's fine. So we did it. Questions, comments? As long as it doesn't break things, yes. Yep. And a lot of times knowing what that K is, like K is going to be restricted in a way that allows you to do stuff, right? Like the last one, multiplying, I don't know, 3 times K had to be smaller than K squared because K is bigger than 5, right? So they're equal to it, so it works. Just like getting this to a place where things, they don't fall out for you. You've got to get them there, but. Is that okay?
What is K?
Is it? Is it a K or is it some other thing?
Maybe because of K plus 1, so. Something K.
Yeah. You're good? Sort of good? Sort of fine? You're understanding that this is probably because it isn't obvious, is the hardest part of doing these. But also allows you the most opportunity for creativity. Who's been messing with all the ceiling tiles in this room? Why are they all messed up?
People been hiding them.
But why? Okay. To do this one, y'all, we have to do K plus 1 to the 5th. Which I don't particularly think would be useful to do right now. We have to do, look, you see, we have to do K plus 1 to the 5th minus K plus 1. I don't want to do that. Then but the like K to the 5th and the K will fall out of that, which you know is divisible by 5. So that's how you're gonna set it up. But I don't want to be doing it. K plus 1 to the 5th. I'm gonna use a little triangle thing to get all the coefficients, but I don't want to. Y'all want me to put that up for you later? On the internet? I can do that.
Take the sleeping medicine.
Huh.
Great. I don't know how to feel like anything.
We're doing a lot of things, Charlotte.
I skipped over like 3 problems. This is great.
It's also a matter of, I want to cover this section and have time for it to marinate before your test. We could take a test Tuesday, but I think we should probably wait. So it's going to be Thursday, but like this is the last bit. 5.7 is like here, but it's sort of throwaway.
Yeah, we're gonna like skip 4 more problems.
Just
so
gonna
we're be,
skip-
like, done with the whole
We're gonna
packet
skip
by
a
the end
whole
of the day.
section. Oh my gosh, I have to put sets on this test too, huh? Y'all didn't have any y'all didn't have any set proofs on this, on your last test. No, you did not.
I remember.
I remember stuff from sets.
Yeah, I'm pretty sure there were.
Just trust me.
I think it's that medicine.
I won't remember this conversation anyway.
So now we're gonna get confused.
Everybody's gonna be confused.
That's
Um,
getting to you. You're misremembering everything.
Yeah.
So for regular induction, which we have been doing now for like 2 days, 2 class days, is that you assume you can get on you prove you can get on the ladder. And then you assume that if you're on a particular ladder rung, that you can get to the next one. You prove that you can get to the next one. So what that means is, again, think about the domino analogy or metaphor. You have the like first domino is going to fall, and all the dominoes are placed in such a way that this one will knock over its neighbor. Yeah. Okay. Well, strong induction, for this particular domino to fall, you get to assume that all of these dominoes fell.
What?
Yeah. So for regular induction, you need just the domino in front of your domino to fall. Right? So you assume you can get on the ladder. Once you're on the ladder, if you're on a particular ladder rung, you can get to the next one. That's regular induction. Strong induction says you can get on the ladder. And once you get on the ladder, if you can get all of the ladder rungs up to a certain ladder rung, then you can get to the next one.
So it's like starting in the middle instead of starting at the first one.
Is needing more than just one thing to happen. You climbed. Huh.
Okay.
from the base step on.
So this is do normal induction to do strong induction?
So for part of this, like, sometimes. Oh, I wouldn't use that one either. Sometimes things are defined in such a way that like. Oh, heavens.
So like, would this be okay for all the card?
Those bullet points?
Yes.
Yeah.
Okay.
Yeah.
Oh.
The reason that this works and why this works, when you asked a good question, is basically what we're saying, what we are doing is, we are going to, for our base case now, we're gonna do a couple of steps. We're gonna say, we can get on the first, second, and third ladder rungs, yo, and then when we move to our inductive hypothesis, we're gonna say like, well, we know we can do all of these things. We have all of these things, and that's allowed, and then we'll knock over the next one. It's strong induction because you have to prove more base cases and you assume more things are happening. So yeah, and we can just throw in another letter because why wouldn't we? Strong induction is used to prove a statement P of n is true for all n. The main difference is the inductive step. So for the base case, you assume PK is true, or for the base case, you show it works for the base case. In regular induction, you assume PK is true for some K, show the PK plus 1 is true. For strong induction, you assume that it works for all values up to the K you're on. And then you show it works for the K plus first step. So it's not just true for some K, it's true for all values up to K. Right. In strong induction, you also need to prove more than one base case to establish the property that you're trying to prove. Like why, how can this work? How did you get to where you are on the ladder? You have these base cases that allow you to be there on the ladder. Okay. Oh, this is kind of fun.
It's kind of like, by cases, like we're gonna be doing multiple.
Yeah.
cases.
Yeah, for the base case, let n equal 1, 2, and 3. Notice blah, 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 it works for n equals 1, blah, 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 it works for n equals 2, blah, 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 it works for n equals 3. Yeah. This one, we don't actually have to do more than one base case, but this is fun. Are you ready?
Not really.
Yes. So if n is an integer greater than 1, then n can be written as a product of primes.
Oh, we're jumping right into it.
Oh, yeah.
Okay. Got
This is to make a point of why the thing is useful for a big idea, right? You're going to be doing things for smaller ideas. We'll prove by strong induction, period. For the base case. What's our base case here? What's the smallest n can be? We're trying to prove that 2 can be written as a product of primes. Well, 2 is a prime number, so we're done. How's that, Whitney? Better? That so is really small and has 10 to anyway. Just didn't need to be there. Okay. Since 2 is prime, it's already written as product of primes. We're done. Now, here's the inductive hypothesis. Are you ready? Suppose. Oh, sorry, Logan. For all integers I with 2 less than or equal to I less than or equal to K, that I can be written as a product of primes. Okay, so this is the inductive step here, the inductive hypothesis. Remember, we're assuming that P of I is true for all I up to K. So for all integers I that are between our base case and the number we're on, that this works. So assume that it works for all I up to K. And that means that I can be written as product of primes. So that's the thing we're trying to prove. We okay? Yeah? Are you? Yes, maybe so. Yes, okay, okay. Consider the integer K plus 1. If K plus 1 is prime, we are done. Hi, Alessandro. Do you want to help do the proof here that any number can be written as product of primes if it's bigger than 1?
Oh, I'd love to. I can try at least.
I took some cold medicine earlier and it is, I'm having some difficulty.
Oh.
Yeah, it's fine. Why did you choose not to sit in that chair?
What?
What was wrong with that chair?
I was just pushing it down.
Oh.
Yeah.
Just cleaning.
Mhm.
Okay.
That's it. I don't even know if I remember it, but. How
This
are you
is
doing
a
it?
fun proof.
Strong induction.
Strong induction.
So you can make small numbers that are products of primes. So you can make bigger numbers out of those.
That are products of those products of primes. That's right.
Yeah.
That's how you do it. Okay, so we have this integer K plus 1. If K plus 1 is prime, y'all, we're done, right? If it's a prime number, it's already a product of primes, we're done. If it's not prime, then what do we know about it?
I think he said.
That thing he said, that it's composite. Yeah? What does it mean if K plus 1 is composite?
And it has factors.
Good, yeah. And what specifically about those factors?
Prime factors.
No.
Okay.
M and N. It has factors. What does it mean for those factors? For the thing to be prime, it means those factors are 1 in itself, right? So if it's not prime, then those factors are not 1 in itself. Hi, Bryson. I love your shirt. I would like to have one. Where did you get it, Bryson? Of course it was. All the best math things are gifts that random people find.
Have you seen my, sometimes I go off on a,
Yeah, I had that shirt.
yeah?
Yeah, it was given to me by some students, yeah. I like that one, but the it's all fun and games, so somebody loses an eye. It's a perfect shirt. Okay, as soon as I saw it this morning, Bryson, I ran upstairs and told my husband about it, and so anyway, okay. So we have this K plus 1 is written as a product of 2 things. Those 2 things are strictly between 1 and K plus 1. Right? For it to be composite, they can't be 1 and K plus 1. They have to be strictly in between there. Yes?
Yes.
Okay.
Oh, so we're restricting. the in-
Because it's composite, right? It's not prime, so they're not 1 and K plus 1. But, how can we make that inequality not a strict inequality? But rather or equal to an inequality. What did I do? But if I add an equal sign with the 1, then I might break it because it might be prime. How could I change it and add an equal sign? If it's not one, if it's strictly bigger than one, then it is bigger than or equal to two, the two. If it's an integer, yes. Okay, cool. Oh, I should have said that those m and n are integers somewhere.
Could you just put, like, this thing, like, in all of the, after the whole-
Right, we backed off on we got bigger than one and we got smaller than k plus one so that we could say the or equal to part. What's true about m and n, y'all? Are they i's?
Yeah. Yes, oh, they are.
And there's two of them, so they can
Oh,
see.
they can see. They are i's, right? And what does that mean? Yeah, yeah, but like, for m in particular, since it's an I, what does that mean? Cool, and since n is also an I, what does that mean?
Can also be written as
Cool, so
part
what's m times n? A product of primes, which is a product of primes, we're done. We did it, we did it, we did it. Okay, so,
Transition word, looky here.
looky here.
Is that valid for?
Is that valid?
Yeah,
Is it too
I think that
formal?
you actually used
I
that,
probably
didn't
did.
you? Yes. I don't mean like if you were writing a textbook, somebody would change it, but.
Publisher would be like,
Like, is this test valid?
Right. Okay, for the test, it's valid. Yeah, for sure. I would love to have a little giggle while I'm grading your test. So thus, m and n can be written as a product of primes by the inductive hypothesis, which I didn't call it that, but that's what it was. Therefore, k plus one can be written as a product of primes. Well, I should just go ahead and make that really over the top by calling that m times n. Okay, so this is our first proof with strong induction. Hold, I shouldn't talk and try to finish this proof. Hold on. So any integer greater than 1 can be written as a product of primes. Okay, so my question for you, once you're done writing and then you have an opportunity to think, is what made this different than regular induction?
We had two variables instead of one.
Oh, well, that's true. That's true.
It's a lot longer.
Okay,
My hand is in a lot more pain than.
okay, good. The thing I was really pushing at was close to what Ruth said, right? Like we had to use the fact that everything beneath K fit this thing, we needed more than just the ladder rung before the one we're trying to prove, right? It doesn't just help us to know that the number before K plus one can be written as a product of primes. We need to know that some factors of K plus one can be, right? So we have to know that all of the dominoes up to the domino that we are trying to work on have fallen, right? Yeah. So that's the difference between regular induction and strong induction, is that you need more, you have to assume more, and you need more to show that you can get to the next step. Okay, questions or comments? Now, your homework 9 is just regular induction. Strong induction is not till homework 10. Yeah. I think.
What else to do?
I sent you an email. I said, Charlotte's not gonna be able to write this down. She's gonna write it down wrong. Yeah, no, you're, I honestly don't remember what I put on there.
I don't even remember, I wrote it down, but I'll.
Is it Sunday, Saturday, Sunday, Monday? When is your homework due?
There's something over the weekend, but
What?
I just turned it in during class.
On Tuesday? No. Well, I mean, if you don't want any feedback, okay, sure. You should want feedback.
24th and 28th.
Yeah, that's Sunday and Thursday. 24th is Monday and Thursday. You can just hand it to Julia on Monday. Or me. Okay. Bring it to the president's inauguration with you.
I'll give it to Dr. Foster.
There you go. He can get it to me somehow. Okay,
Did Dr.
sounds.
Emily Thomas come to the state?
Let's just hope I'm there. Okay. Shall we do this one? What time is it? Oh my gosh, I did not know it was 3:20. No, okay, fine. We won't do anymore. Okay, so homework due Monday. Really, I'm giving 2 tests on Tuesday, so I could grade your homework on Tuesday and I'll hand it back to you in class. That's my goal. That's my plan. So, I would love to have it before then so that I could check that off my list and not add it to the stack of grading that I'm gonna get on Tuesday.
What if we just cancel the test?
I can't.
Hundreds for everybody.
100 for, oh, that'll be fun.
Your
I would
tests
need
or
100.
theirs?
Or zeros for everyone.